We are running behind the schedule. So hopefully you all guys, you did your submissions. How was it? What are the gigaflops you are getting?
6,000.
Huh? 6,000 for Q? This is the collab. This how much? Sorry, 6 teraflops. 6,000 gigaflops. For single precision or double precision? Double precision? 2,000. 3,000. You got half.
What's the float 64 compared to float 30?
Float 64 compared to float 32. Okay, so how much?
So at 8,500 on float 32 and around 4,200 on float 64. The peak
Okay.
performance.
4,000 gigaflops. So it's a teraflop, okay? Back, yes. Okay, doesn't matter. We'll get you another chance. Okay.
But it still was like 10 to 15% below the theoretical limit even after increasing it as much as I wanted.
Yeah, but that is the overhead in data transfer and all of that. 10 to 15% is okay. And how much is the CPU flops?
Sir, 270.
270 gigaflops
Yes, for a NumPy.
for NumPy. And for Python loops?
0.03.
0.03. And C?
10
10 times. 0.27. So you know how to now why to use NumPy. Right? 2.7, right? 3 gigaflops if you just use a naive C code. And if you use Python, it's like 10 times slower. But otherwise, if you just do NumPy, SciPy, you can get up to what? 270, right? 300 on an Intel machine. And from 300 to 3000, that's a 10x improvement. Right? That's where NVIDIA stock is where it is today. And that's where machine learning is where it is today. Right? Deep learning. A lot of these innovations have been made possible because you have these very fast GPUs that can train your networks, do this forward and back propagation very, very efficiently. And last time we saw both forward and back propagation is a matrix vector operation or matrix multiply, matrix or a matrix vector operations. And these can be done very efficiently. We are saying that it's about 85% of the theoretical peak performance, which is awesome. This is really very good. In general, you cannot get that kind of performance. Typically, you get like 1/5 of the peak performance and all. On the CPU, how much is it? How much of the theoretical peak? Huh? CPUs, you are getting 50%. But maybe you can get slightly better. Maybe you can use a better library instead of, maybe your library is not optimized for the CPU. You can actually make a specific library optimized for the CPU. And then maybe you can get up to 80-85%. Huh? It's already using multiprocessing. If you are using that library, it has multi-threads and multi-cores. So all of that is being used in the library.
Just naive Python will not use multiprocessing.
No, naive Python will not use. Okay, fine. So today what we are going to do, oops, what happened? Did I get a wrong version? Okay, so today we are going to look at some tricks to optimize your learning in the neural networks. And some of you may have already done it, but I think we'll do it very fast. And then if you cannot finish it, I'll just give it to you as a reading assignment. Okay? So this is a general architecture of neural networks. It can be very deep, multiple layers. To do the forward propagation, we just multiply with the weight vectors, with the weight matrix, get and apply the activation, add bias and apply the activation, you get there. Model parameters are weights and bias at every layer. And then there is a loss function to the last layer. It could be squared error or cross entropy loss, or it could be any other loss function that you can imagine or design. And typically what we do in machine learning, which I personally don't really like, being a little bit more mathematically inclined, why should you just sort of, settle to a local minima? But we want to minimize this function. It's a very non-convex, very complicated function. We can't really get to a good optima, so we just apply gradient descent and then try to settle into some local minima. Need not be the best, but interestingly, on real problems, on the architecture that we designed, it seems to give excellent results, right? So the proof of pudding is in eating. It's like, when Wright brothers built the aircraft, they didn't know anything about aerodynamics. They don't know anything about, Navier-Stokes equations and blah, blah, blah. Yet they made something which flew, and then later scientists discovered that what are the laws that actually govern this. We are in the same stage today. They just engineered a network architecture, engineered a way of learning the network, and it just works. But we don't understand why it works. So hopefully in the next 10-15 years we'll get more innovations that will tell you how it actually works, and also we'll get improvements in the performance and improvement in the architectures. So, oops, I think I got the wrong version. Wait. Sorry, okay. So when we do back propagation, we look at the gradient descent, and we saw that the gradients were the sum of the gradient for each example, right? So there are three versions or three variants of gradient descent that we'll discuss. A batch gradient descent, where you will compute the gradient with respect to all the examples simultaneously, and then you back propagate it, update the weights, and then recompute the gradient. Stochastic is the other extreme, where you just look at one example, pick an example randomly, find the gradient, update the weights, and then pick another example. And I think both of these methods are kind of not good, because batch gradient descent takes a long time, because every time you have like 50,000 training examples, you are computing losses on this, doing a forward propagation and doing a back propagation. And just going over all the data just once gets you only single iteration. So the way the loss decreases is very, very slow. Now stochastic gradient descent, you can just look at one example and quickly find the forward and the backward propagation, find the gradients, but it is not the representative of a whole sample. So again, it does not really converge very quickly. I mean, it is better than the batch gradient descent. So typically what we do is mini batch gradient descent. So I think there is some issue.